Okay, so hello everyone. Uh, okay, so do I have a voice? Can you hear me? Because it's very hard for me to check if everything is okay. Yeah. Okay. All right. Thank you so much, everyone, for showing up today again. We'll continue with our second lecture. Uh, um, Yeah, and the first problem set I hope is going to be available this week. Okay, and just start doing the exercises from the syllabus so you can get used to everything that we introduce. Yeah, okay, so we take up the example from the last class. Um, yeah, we will continue on that. So we just, yeah, so you're talking about, yeah, it's really up to you. I will upload the notes. I will scan them and then just upload them. I will also put the online video on my YouTube channel. As I said yesterday, it's still uploaded, I think. It was too long. Yeah, it was too long, so I had to trim it a little bit uh, just to remove all of the down spots. Yeah, so I think it should be available today. And for the notes, yeah, probably today. By the end of when I will finish the class, I will just scan them. I just wanted to do it like in one shot, and not like have to do it two times. So hopefully today I will scan everything. And yeah, but the good thing about the notes is if you just want to go to the point and just see instead of reading the whole book and going around. Okay, so I really have to keep track on people who just join the meeting, and that is very hard to do, but I will try. But try to sign up earlier because there is no guarantee that I will keep clicking on, I will keep admitting people as I will be explaining the material. Okay, so remember that yesterday we talked about double integrals. So we'll just go over what we did since this tends to be a good idea. So we went over double integrals. We introduced what is a double integral. We've seen that it's the same thing as in the one-dimensional case. It's exactly the same idea, but you just extend this idea to rectangles. You divide them, and then you introduce the double integral as the limit of this all of these small volumes that you start adding up. And when this limit exists, uh, we call it the double integral. Now, we then talked about how we can actually compute this integral. So we introduced let me just try to just go some kind of, yeah, yeah. So then we've seen that we can do some approximations, but that is not enough. So we talked about iterated integrals. So these are just one-dimensional integrals But when you fix some variable and then you see the function uh, here as a one variable function, and then you integrate as you do in the one-dimensional case, you get these functions of x and y, and then you integrate them again, and then it gives you two integrals. And then we did the same thing from the other way around. And then we introduced this Fubini theorem, which says that this double integral that we're looking for is exactly the same thing as this iterated integral or the other one, uh, provided that the function is continuous in the rectangle, which will be the case in all the functions you will be asked uh, to compute, almost all of the cases. Yeah, and then we gave a kind of little convincing argument, I would say, why this works. Because this AX and this AY, they just give the another way to compute the area times the height of this very cylinder. And then we gave some examples. We've seen that it's not that hard. And then we started talking about double integrals over general regions, which means that if I have a region D that is not necessarily a rectangle, then we wanted to do also the volume that lies above this D. So the way we did this is we use what we know about what it means to be, what is an integral of a rectangle, and then we use the fact that these are in general bounded regions. So we bound them by a rectangle, then we introduce a function that is zero outside this region. Here is zero, and here takes the normal value of the function. And then if you want to integrate this function on D, then you just have to integrate this capital F on R. And then we use one, so for, and then we introduce type 1 regions. These are regions that look like X is between some two real numbers, but Y is free to vary between some two functions, some two continuous functions. So this is an example, and this is another example. And then for this kind of regions, we use one version of Fubini's theorem, namely the one that starts with dy and then dx. That is the easier, that is an easier way in this case. So, and then we just observe that when we are outside D, this function is just zero. So actually you don't need to integrate from C to D, you just need to integrate um, from the boundaries of D, which is G1 to G2, and then AD is a constant. So for this kind of regions, this is how we compute the integral. And then for type 2 regions, we do exactly the same thing. It's on the other way around. You just have to, so, you know, X plays the role of Y and Y plays the role of X. And you do the same thing. And then now, instead of starting by dy, you do by dx, then you realize that that is the right way to do it. And then we did an example, which is find the area, okay, now we wanted to integrate a function actually over this region D, given by the intersection of this parabola here and this other one. All right, so we did that yesterday, and so each time they ask you to find the intersection, each time they ask you to find a region, you start always by finding the intersections. That is the first thing you do. Okay, now for two parabolas here, the intersection is given by this equation here, which is x equal to plus or minus 1. All right. So the region that is between these two curves is uh, the yellow region here. Okay. All right. So and now we observe that it is a region of type 1 because for some x fixed, y varies from this function here to this function here. All right, so let's continue on this example. Okay. Uh, okay. So the region B is given by B equal to, yeah, I'm sorry, because I'm supposed to do it on the same. Uh, can I do something? Hmm. Let me try something, just to not confuse you, because it's really important to stay on the same page. So let me do something. Can I have a screenshot here? No. Um, oops. Let me do something quickly. 11 plus 365. Okay. Save the photos. And then, all right, good. Technology is good sometimes. Cool. Okay. So the region D, so the region D is given by all the elements X and Y such that, oh, such that um, X is between -1 and 1, and then Y is between the function 2x squared and 1 plus x squared, right? So, so if I want to integrate this function, d over d to y to the a, right? This will give it this, so this will be given by the integral of d to y, d, and here it's x, and here it's y. So here it's dy dx, all right? Now, when you fix some x is between this curve and this curve. So it's between the curve 2x squared and 1 plus x squared. Now, what is x? X is allowed to vary from -1 to 1. Okay? So that's the integral. And now once you've done this, everything is, just be careful and do the calculation. So Now integrate from -1 to 1. This is a function, elementary one. Between here, you need to be careful again. Y is between 1 plus x squared and y is equal to 2x squared. Okay, and then you integrate everything that you get with respect to dx. Okay, right? So this is the integral from -1 to 1 of 1 plus x squared minus 2x squared, right? Dx. Okay, use the same trick. Okay, so this is 1 and this. Oops. Okay, okay, y is smaller. Sorry, was it a typo? y y is smaller than or equal to 4x squared. It is, I don't see 4x squared. It's 1 plus x squared. Here is 1 plus 1. Oh, this is not 4. This is 1. Oh, I need to be more careful about. This is 1. This is 1. Why do we need to use a double integral? Um, well, like, what do you mean? Uh, I mean, this is a double integral. So we don't really need, I mean, if this is a practical problem that you can solve only one single variable, then yes, you can solve it. But here we're just giving an example of a double integral. And probably you can do it by one single variable, but I don't see how we can do this here. But here it's just a double integral. Here we're just asking you to compute this double integral over the region D. So just do it. Uh, it's just an example. Not necessarily, but here I don't see how you can do it in just one variable function because it's the this is the volume that lies above this region B. So whenever you have a volume, uh, I mean, if you had 1 here instead of 2y, yes, you can do it with just one variable. Yeah, but we're not calculating the area here. Be careful because of this factor here, right? If I didn't have this one here, then yes, what you're saying is right. You're just computing the area of the region D. And that's exactly what you've been doing in single variable calculus, right? But then when you start uh, considering the functions of two variables inside the integral, then this is not a one variable. This is not. It doesn't give you the area. This is not the area of the region D. This is the volume of the function. This is the volume of the solid, as we said yesterday. This is the volume of the. Well, here it's not necessarily the volume because y is not here. Yeah, y is positive, so this is the positive function. So here's the volume of the function that that is exactly under the graph of 2y, right? And above the region D. So it's a volume, it's not an area. That's why we need to use a double integral. So remember, for area, you will need one variable functions. For volumes, you will need two or three variables, right? Dependent. So this, what we're doing right now is the simplest uh, volumes you can find. Now it's gonna be a little bit more harder when the region D will be itself something 3D, right? So we are just so the regions we are looking at right now are regions that are in a two-dimensional plane, like circle, this type of region. So now when this D will be allowed to be to be kind of a surface, and then you will have a very fancy solid that is bounded by every kind of surfaces from every reach, from every side, then it's going to be a triple integral. Okay, you're going to have three integrals you have to do. That is a bit more harder than this. So this is two integrals, but we're going to get there. Not now, right? Uh, all right. So any other questions? Okay. So we have this. Uh, and then we just compute this thing here, which is just the integral from -1 to 1. Okay, which is equal to between 2 minus between 1 and -1, which is equal to -2 Okay. Okay, so let us do another example. Let me just go. I don't have my glasses. So. Okay, so let us do another example. Evaluate the integral of a d of x, y, dA, where d is the region bounded by y equal to x minus 1 and y squared equal to 2x plus 6. Okay, should we have -3/5? Oh, you mean there? Yeah, of course. Yeah. Thank you. Okay. Uh, okay. So what is this region here? Oh yeah, of course. Thank you so much for yeah. Okay. Okay. So is there any other typo? All right. Okay. So this region here is given by some. Okay. So here we have a function that is a linear function, which is um, goes from the point 1, 0, right? Okay. That's the first one. And then we have a parabola again, which goes from -3. This is -3, and this is 1, something like that, right? So we would like to have the reason here we're talking about is this reason here, right? So that's the reason. Okay, it's the region D. Okay, so this, so again, we have to find the intersection. So here we have a first intersection, and then we have another intersection, and then we have these two here. Um, okay, so that's the reason. So we first find the intersection, right? But first find the intersection, given by when these two functions are equal, which means that 2x² plus 6 is equal to x minus 1. Right? And this is like that, right? And then you can solve this one, which is equal to x minus 1 or x equal to 5, right? So here, this is x equal to, so, so what is the image of each one? So the point for the intersection is, for the intersection, is just 2 points. Uh, the point -1, uh, -2. Oh, the other function is this is y squared is equal to 2x plus 6. And then the other one is x times 1. It's 2x, not 2x squared. How, why? Oh, oh yeah, yeah, of course, of course. Rectangular. Hmm. Yeah, yeah. Yeah. Now, let me check my notes. Example. Yeah, hold on one moment. It's not really. Okay. Yeah, but then this is not the graph I'm looking for. Because I wanted to do something like not y equal to x squared. I wanted to do it the other way around. So, hmm. Yeah, but that is not. Then you just have to isolate x instead of y. Yeah. So I think yeah. Uh, let me remove this. Uh, but let me remove this. So then you have to do it for x, not y. Okay, but then this is gonna mess up with my calculations. So I don't want to make a mistake. Uh, yeah, yeah. It says, hmm, yeah. So the intersection now is given by. Now you just have to isolate x. It's given by, uh, yeah. And now the intersection is given by y squared minus 6. But is this gonna give you same over 2 equal to 1 plus y, right? You guys can follow me if it doesn't make sense for you. And then you will have to solve this one. And hopefully this will be the same thing as, yeah, okay, right? Right? So here it's for my plus, yeah, yeah, it should make sense. All right, so let me just let you do it by yourself, solve this thing, but it's supposed to be, that is supposed to give you 2 points, right? Y is equal to, all right, y is equal to uh, -2 or 4. That's what's supposed to be, -2, yeah, -2. And y is equal to 4, 16, yeah. Yeah, yeah. Okay, so solve it, and it's gonna give you what it gives you. But the idea is just to follow me on whatever this gives. These are the points we're looking for, right? And then x will be whatever. So x here it's gonna be uh, -1, -2, is -1, -2, and 5. Okay. But so the reason I included this example is to make you, not to make you calculate anything specific, but just to make you aware that sometimes you can have a region that is both uh, a region 1, type 1, and region of type 2. Well, the reason is because uh, for some specific x, for example, if you fix some y, for example, if I fix some y, right, and then if I fix some x, right, the reason is for y between -2 and uh, this will be 4. And this is the 0.54, and this is -1, right? So for some specific y between -1 and 4, x is allowed to vary this from this curve here, given by y squared equal to 2x plus x, to the curve y is equal to x minus 1, right? Now, you can also do it for the other way around. You can take x between 4 and here, but it's going to be a little bit harder you have to break it down into two, right? You have to break it down into two regions. Namely, you have to consider, let me draw something. You have to, um, if you want to do it like a type 1 region, you have to separate this region into two, right? Two regions, right? And then you will have to do the first integral, that is a type 1 region, right? Because x will be between -3 and -2. And then y will be allowed to vary from these two sides of the parabola. And then once you get past -2, then the two boundaries will change. They will be, for now for some very specific x, you will have to go from this line to the same parabola. So it's a type. This is type 1 region. This is type 1 region. So you realize that if you want to do it one way, it will take you two integrals, one with a two. The first one will be, uh, will take you will take g1 and h1 to be the same function, right? Which is y squared to represent. But then once you go to the other region, you will have to change the boundary because now g1 will be uh, the linear function y. So it's a bit more work to do it one way. But if you do it the other way, which is a type 2 region, you will not have to change the boundary. It's all the same all the way along. It means that for some specific y, it varies from the same function to the other function. All the same, right? It's all the same, all the same. So that's why you have to be very wise when you choose which one you want to do, right? So so obviously you want to choose the one that takes you less time. So in this case, it's gonna be a type 2 region. So in this case, it is D uh, is both type 1 and 2. But it is easier to evaluate the integral when you see the region D as a type 2. A type 2 region. All right, so here's the description of the D as a type 2 region. So it's all the x, y, such that y is between right? Y is between -2 and 4, and then x is between, they have to isolate x, 1/2 y squared -3 and y plus 1. Okay, so the integral of xy dA over the region D is given by the integral of xy dx, because now it's type 2 region, so we fix some y and then we integrate with respect to x, and then dy. Now x is between 1/2 y squared -3 and then 1 plus y, and then dx is between -2 and 4. Okay, makes sense? So far, so good. If you have any questions, I keep looking at the chat. So don't hesitate to ask me any questions, or you see any error. Uh, if you see something that doesn't make sense, it doesn't mean that it's hard or you don't understand it. It means it also means that I made an error, which is possible. Why is it that dx dy? Oh, thank you so much. The good thing about people who ask questions is I like it. So it's dx dy because it makes it very easy for me. I know that there's at least someone who's following me, so thank you so much. Uh, all right, so let's continue on this one. So now, once you've done this, just be careful. -2 and then 4. Uh, now it's x squared. Now y is fixed, right? So x squared over 2y between x equal to 1 plus y, and then x is equal to 1 over 2 y squared minus 3, and then the whole thing will you integrate with respect to y, right? Yes. So yeah. So the question will give us the integral of this function here. So once again, if you didn't have this xy, you will be just computing the area of D. But because you have this function inside, this is the volume of the function, right? And it makes sense because when xy is equal to 1, you are just having a cylinder with basis D, right? It has the volume, it has the area of D, right? You just multiplying, it's just the normal, the high school formula. It's the area of the base times the height of your cylinder, but in that case it will be 1, right? So it's the base of the area times 1, which is exactly up to uh, units, right? It's not the same units, but it's the same numbers, right? So that's why when you have 1 here instead of xy, it just gives you the area. I mean, literally speaking, it gives the volume of the cylinder with base D. Means that you're gonna just translate D linearly along the z axis, the z axis, which is a cylinder with base. Whenever you have a cylinder with circle as a base, or whatever you have in the base, you just multiply the area of the base times the the, the height of your cylinder. In this case, it will be the area times 1. That's why it gives you the area. But now, because we have this factor xy, it is no longer a linear stretch. It's like kind of squeezing, like I don't know, it's kind of weird motion you do to D once you go to the z-axis. So it's no longer something nice. So that's why you really need two variable functions, right? It's the kind of motion of D, and whatever you get when you have this motion, it's a solid, right? And of course, the top is also a function that is a surface area of a function. So it's not something as basic as multiply the area times something. Uh, okay. Uh, okay, let's stop. I'm not gonna make any error. Well, okay. So this is equal to 1 over 2. Uh, the integral from -2 to 4 uh, y. Why should I have one over two here? Uh, yeah, because I just pulled it out. Okay, it's y, 1 plus y squared minus 1 over, oh, I think I have a calculator. Uh, yeah, it's supposed to be, it's 1 over 2 y plus 1 minus 1 over 2, oh, no, no, right? Let me just check if I have everything okay. X is there. Yeah, I think I'm right. And then the whole thing integrate with respect to dy. Okay, so this is the competition. You just do it. It gives you, okay, oh, I'm not gonna do it carefully, but uh, it's you do it. You do it. It's again like a lot of calculations. It's 1 over 2. You know how to do this. So it's 1 over 4 and 6, right? Plus y, right? Yeah. So the point is not to do these calculations. The point is to understand how to do it. So hopefully this is all right for you. Okay. Yeah. So here's the a very, very interesting thing that happens with, that is a very, very surprising thing. And one of the most good things about changing the order of the integral. So in some cases, you can encounter some you can encounter some double integrals over some regions, but you cannot compute it. It's just hard in terms of finding the antiderivative. It's not possible, right? But when you change from type 1 to type 2, it suddenly becomes easy to do, right? In one way, it's impossible, as we're going to see in this example. But once you change the order, it becomes possible. That's a really something surprising. And actually, you're going to see an example of it um, in the problem set, which is an applied, which is applied to probability. Uh, there's another example of this, and calculate the partition, the, the one very, very useful integral that we use in probability. So here's an example. That's it. There isn't like that much of examples like this, but here is an example. Evaluate. So evaluate uh, this integral from 0 to 1, and then from x to 1, sine y squared dy dx. So that's the question. Evaluate this thing. There's no region, nothing. So now you have to go backward, which means that from the integral, you need to find the region. And then once you find the region, change the type of the region, right? Because if you just want to do it like just on the spot, just looking at this integral, it might be hard. You need to visualize this domain here, D. So let's do it. So obviously this is an integral over some region D that we don't know yet. Okay. So well, this takes a little bit of practice to get used to what it means when you see these integrals. But the region here is it's a type 2 region, right? It's a type 2 region. Uh, we want to, no, sorry, we want to do it as a type 2 region, but it is actually a type 1 region, uh, right? For some fixed y, for some fixed x, y's, all right? So D, oh, sorry. So D as a type 1 region, right? D is given by D is all the xy such that uh, x is between 0 and 1, and then y is between x and 1, right? So if you try to plot this thing, uh, so we have y equal to x on one side, we have y equal to 1 on the other side, right? So this is 1, and this is y equal to x, right? And then we have x between 0 and 1. So that's x, right? So this is x, this is y. So again, the region that you are looking for is this region here, B. So it's here, right? Because I believe it's the region B. Oh, could you please write them on the same page? Is it possible to keep the letter while you write on the new page? Oh, so yeah, that's exactly what I did. I wanted to start on a new page, so I had this space here, but I didn't use it. So let me just write. I'm gonna recall this integral, but just to make sure that you understand that you have it. We are trying to compute this integral here from 0 to 1 x1 sine of y squared. Okay, you are right. Yeah. So that's the region D, and then it's expressed as a type 1 region, right? Okay, so that's type 1 region, type 1. Now, as a type 2, so yeah, so the first thing to, to, to observe here is that this is not possible to do. This integral is not possible. That you cannot find a primitive function of sine y squared. It is not an elementary function. You can do it by power of series. It's possible, but it's not going to be it's going to be an approximation. You can develop the sine y squared into uh, power series and try to do it if everything is okay. But by integrating each term, that's another thing you're going to do a problem set, but uh, it's not going to be a function right? So let's try to change the domain and see what happens. So this is not possible to do. Like there's no way you can compute this exactly. So now, so as a type 2, all right, let me take a break, I think, of 10 minutes right now. All right, let me take a break and we'll be back at 11:23. 11:23. Okay, let me just write it somewhere. Okay, welcome back everyone. Uh, let's continue on the example. So we would like to express the region D um, as a region of type 2. So as a type 2 region, D is given by all the elements x, y in the plane, such that so what? So now we'll go for each fixed y, right? Now for each xy and for each fixed y, right? Um, so so y is between, and then x is between, and then something. So normally what we do is you would, here it's very easy, right? Because y is equal to x, but normally you would isolate x. You would just solve for x, and then you would do that. Right? For example, if it was like y is equal to x squared, you would say x is equal to square root of y. But here it's y equal to x. So for some y, x is between what and what? Well, for some y, x is between 0, then for this very specific y, between 0 and 1. Right? Now, as you go and you vary y, that's another y, uh, right? Y is allowed to move from 0 to 1, right? So the integral by Frobenius theorem, the integral from x to 1, 0, 1 sine y squared dy dx is also equal of the same integral, same function, but on the region D as viewed as a region of type 2, which means that I will start by integrating with respect to x and then with respect to y. Now x is between 0 and y is between 0 and 1. Now suddenly, what you can see here is we no longer have this problem of finding the primitive of a function that is not elementary, because now y is a constant, so now I can do it. So this is the integral from 0 to 1 of the function x or the function y, right? So it's a function, the function x sine of y squared between x equal to 1 or y and x equal to 0 dy. Trying to find if there is any feature. No. Um, okay, I'm just gonna wait if anyone has any question. Okay, so we're gonna continue on the last line. Uh, sorry, I will try my best to be on the same page, but sometimes it's very impossible. So this is, so if you evaluate this thing here, so, so if you evaluate this thing here, if you plot x equal to y and x equal to 0, it will give you this. Okay, and then once again, this is also something we can compute, right? This is just, yeah, plus 2y squared, right? Just change of variable, normal change of variable, right? And it's 1 over 2 minus, right? And then from 1 to 0, which is 1 over 2, 1 minus plus 1. See? So as strange as it might look, but who would have said that this function here that we couldn't do in an elementary way gives something that is elementary. That's one of the good things about it. Okay. Uh, so for today, we still have, so the plan for today is to finish this integrals over general regions, and then go over applications, and that will be the plan. So let me do one last example of another kind of questions you will be asked to do sometimes. Example. So far, I have been giving you a region D, uh, and either I gave it to you or I told you some very easy way to find it on the D plane, on the XY plane. Um, in some other cases, they will not ask you to do. It won't be as easy as that. In some other cases, they will just ask you find the volume of a solid, and then you will have to find the region D under the solid. For example, one very classical example is pyramids. Uh, it's tetrahedrons, right? So for example, consider the plane. Two x plus y plus z is equal to 4, right? Now, let us find the volume of the solid enclosed by the three coordinate planes and the plane P. See? So in this example, there is no find the region D between two curves. There is no compute the integral, right? That's an example. We give you a region and then we ask you to compute. We can ask you to find the region in the two-dimensional plane. In this example, it's another example where you will have to find it from the solid itself. It's not given to you. So the good thing to do here is to draw a three-dimensional figure. Okay. So here we have the three. Okay. Okay. So the first, we have three planes. We have the first plane here, uh, the x, sorry. So we have the YZ plane, that's the YZ plane. We have the XZ plane, and then we have the XY plane, right? So these are two planes. And then we'll have another one given by the equation 2x z, let me move this one here, z, so we have to find this, we have to find a nice way to plot this thing. Z equal to 4 minus 2x minus 4 minus minus y, okay? Okay, so when you have a plane, it's always good to, one of the tricks that can be used to have a good idea of what the surface looks like is to start going by, you put 0 somewhere and see what happens. So for example, if I put z equal to 0, this means that I am restricting the surface of the plane on the xy plane. So when z is equal to 0, here is just my explanations on how we do this in general. In all kind of surfaces, if you want to have an idea of how it looks like, start by going slowly. Z equal to 0, and then y equal to 0, and then x equal to 0, and see how it looks like. So for example, let's give it just to give it a try. For example, when z equal to 0, what are the points x, y, z that will satisfy this equation? Those are the points that satisfy y plus x is equal to 4. So this is a line, right? This is a line. Now, when x is equal to 0, right, y is equal to 4, right? So here we have 4. Now, when y is equal to 0, x is equal to 2, right? And it's a line. So it's a line that goes through this point here. Okay? And now we do the same thing. When, for example, if I project on the xz plane, it means that y is equal to 0. This means that this means that z plus 2x is equal to 4. So once again, when z is equal to 0, sorry, yeah, when z is equal to 0, x is equal to 2. Okay, so the plane goes through this point here. And when x is equal to 0, z is equal to 4. So we have 4 here. So it's a line that goes through these 2 points, right? Okay, and now I do the same thing for the last one. When when x is equal to 0, it's z plus y equal to 4. Okay, so now it's 4, 4. Makes sense, right? So when z is equal to 0, y is equal to 4. And when y is equal to 0, so it's a line that goes through these 2 points here, right? And so so the area we're looking for, so that's the solid here. So that's the plane here, right? That's the plane. Okay, that's the plane. Uh, right? So the solid we're looking for is exactly this one, the tetrahedron between these 3 planes and this plane here. Now you have, what is the region now? Now the region, all right. Uh, so now you have to be very careful because you have to remember the definition of the integral. The volume, you have to find the function. You have to first find the domain D. This is the D. And then right above D, there is this plane here given by z equal to 4 minus y minus 1. It's kind of, it's exactly the surface that is above D. So let me just do it on D. So this is the region D. Okay, so this is the region D. Okay, so for the volume, is it clear for the volume? And this is the solid S. So the volume of S is what? Because that's the point. Above each point, there is a z equal to 4 minus y minus 2x. The volume is given by volume of S is equal to the integral, right? It's a double integral of z, right? Z, this is equal to f. Let's make sure that we all understand what we're doing. This is equal to f xy, right? We call it z. So it's z dx dA, right, over d region d, okay? Which is the same thing as the integral of 4 minus y minus 2x, right? And then you have to choose. Now you have to choose either you start by region 1 or region 2, right? Okay. Yeah, 1 second. Okay, so this is our region, and our computation will be this, right? All right. Now, now you have to decide which. Now you have to um, do another draw another figure on the two plane to see how it looks like. If you can do it quicker than this, then that's fine. But just, we are here to explain the idea. So we are on the X plane, and we are right. So what I'm doing here is I'm taking this I'm taking this and this is how it looks like, right? So I'm projecting on on the two. We're just looking at we're switching the view on a kind of XY plane. So it looks like this. So we have 2, and we have 4, and then we have the line, right? And then we have our, which is the region B, right? Now you have to choose which one you want to do. You can do both of them here, but they will give you the same answer. So for example, if you want to do the region 1, that type of type 1 region, uh, this you have to, right? Right? And remember, what is the equation of this line here? It was 1z equal to 0, so this is 4 plus y. No, this is y equal to 4 minus 2x. Remember, that was the 1z equal to 0. Well, this was the line, right? So the volume of S is equal to the integral of 4 minus y minus 2x dy dx, right? Now, when you fix y, x is between 0 and 4 minus 2x, and then x is between 0 and 2. So that's the volume. Okay. Now we compute. Uh, I will do it a bit quicker here. It's really an elementary calculation. No, no, sorry. Dig it over. No, sorry. Okay. Because why not 0 to 4? Oh, sorry. Is it 0 or 4? No, it's 2 actually, because x on the boundary is, yeah, it's not 4. Yeah, 4 is for y. 4 is for y. Uh, See, this is not x, because x is x, because look, it's always fix some y. Then y is between 0 and what? It depends on y. So fix some x. So y is between 0 and this number here. That depends on x. Okay, now once you fix this, what what is the freedom of x? X is between 0 and 2, right? That's the freedom of x, right? But each time it gives you a line. Each time you fix x, it gives you a line. Each time it gives you a line. Each time it gives you a line. So that's why it's not 4, it's 2. Thank you. Okay. Well, let's do this quickly. Okay, this is the integral from 0 to 2. Now compute these things. Okay, and always check that it's a positive number, right? At least when the integral has the meaning of a volume. So I think I've seen some people, uh, they get a negative number for a volume, and they say, all right, the volume is minus what? Yeah, it's possible in another dimension, I think. Another volume equal minus 1. All right, so, okay, let me just do over quickly. Oh, maybe we should speed up a little bit, because we still have 1 hour and we need, oh, maybe we should speed up. Okay, properties of double integrals. All right. Okay, so there are some properties that you can use for double integral. We're not going to prove them, but they are really very intuitive. The first, all of them, if you just think about the volume, you're just gonna simulate them. For example, there is the first property which says that the integral over a domain, and all of these they hold if the function is continuous and all of that. But if you, for example, have a function fx, right, and then you have another function, right, and then you want to compute the volume under this, you just have to add the volume. So these are functions, these are properties that you're allowed to use, right? Right? Then there is a second property which says that if you have a volume, and then if you scale, rescale the function, and then you compute the volume, you just have to compute the normal volume of the function, and then you multiply everything by the constant c, right? That is right. right, for some C in a real number. Then there is the third one, which says that if I have a surface that lies a bit higher than another surface, and I want to compute the integral, the volume under these surfaces, uh, then one will be larger than the other one. That's obvious, right? So then we will have that the integral of d of this function here will be larger or equal to the integral over d of this function here. And then, yeah, then you have the fourth one, which says that if I have a domain, right? If I have a domain, if I have a domain here, and then I break it down into two domains, which is D, and then I have D1 and D2, and provided that the boundary is thin in a very specific sense. Oh, you missed property 3? Yeah, so property 3 is if I have a function that is larger than the other one, then the volume of one will be larger than the other one. So the fourth one is if you can break down, well, we did that. I explained this in an example, but if you can break it down into two domains uh, with a thin, in a very specific way, which means that it has a measure zero, but in our case, it will be just a line. If you can break it down, yeah. The property tree is this. Yeah, so if you can break down domain into two, and, and then you're going to separate them by a line, then you can perform the integral over the first one and then the second one. Because the line doesn't really count. It will not affect the integral. That's what we mean by a thin set has measure zero. Okay, did everyone get the property tree? You good? Oh, oh, okay. All right, all right, all right. Thank you so much. That's a nice idea. Okay. All right. So the property for is if all right, if D is equal to D1 union D2, right? With D1 intersection D2 is some this line, or I'm just gonna call it a line, then uh, you can integrate the integral of f xy dA will be the integral over d1 plus the integral over d2. Okay. Property 5, I've already explained this one. The area of a region D is just this thing here. Instead of function, we have one. And I've already given the reason of why this is true. It's because of the cylinder and linear translation of the base. Okay, now P5, P6, if a function, this is exactly the same thing as the reason of why if one is larger than the other one. You know, because if a function, the surface is between two boxes, for example, this is a box, right? Okay, and some constants, right? And that capital M is in some real number. Okay, so you have a surface, and it is uh, above some small box, and there's some bigger box. Then what? And if you wanna, then you can have an idea of what it looks like, the volume, what the volume looks like. So the volume will be something, some number between the area of the basis times, that's exactly the same idea. The area of the basis times the height, which is m, and then less than the area of the base times capital M. So these are six properties that you can use uh, if you have any fancy example, and you can just simplify it by using subtracting or adding or multiplying. These are very simple facts. All right, so let us go through uh, section 3, in my case. Okay, double coordinate in polar, no, sorry, I meant double integrals in polar coordinate. Okay, so I would assume that you've never seen a polar coordinate before. We're just gonna recall what is a polar coordinate. So what is a polar coordinate? All right. So each point on the plane, right? Each point on the plane can be described as the point equal to x, y. These are Cartesian. These are Cartesian coordinates. Uh, that's one possibility, right? Now there's another one called the polar coordinate, which means that if I want to give a description of this point, I will give you the angle theta here, right? That's another description. I can give you the angle theta, and I can give you the radius r of this. I can give you the radius r, and then I can give you the, the angle. That specifies the point, right? Either you give me x and y, or you give me theta and the radius. And of course, there's a relationship between them. That relationship is given that um, uh, x is given by, if you use here, x is given by r times cos of theta, and y is given by r sine of theta, right? And theta r is some uh, number r positive, right? And theta is some angle between 0 and 2 pi, right? So the good thing about polar coordinates is that they can provide us a way to compute uh, some integrals over other regions. Of course, you can use the type 1 and type 2 regions, but in some cases, it's not going to be possible. So polar coordinates, they're going to provide an easier way to describe a region. So suppose you have, so in polar coordinates, so what is a rectangle? What is a polar rectangle? So this is a rectangle that looks like this. If we just try to do the same thing as we did with x and y, so we'll be having r and theta, where r will be between some number AB. Remember, we did the same thing, A, B, C, D, right? And this was given as a rectangle. Now we're gonna do the same thing with R and theta. And now theta will, let's say, instead of CD, we're gonna call it alpha and beta because these are angles. Angles are in general labeled by this Greek alphabet. All right. So, so concretely, what it means that I will have, right? Then I will have, right? Then from here to here, I will have, from this line to this line, it is theta between alpha. And then from this line to this line, I have beta, okay? And then if I measure the distance from the origin, I will have if I draw a circle, I will have A and A, right? This is A. Then I will have B, and then I will have B. But I'm talking about the radius of the circle. So this is R, right? So what is this rectangle? This rectangle will be something. It has to be between alpha and beta, which means that I have to stay between these two lines here, this section of disk, and then I need to stay between the radius A and B, which means that I need to stay here, right? So that's the rectangle R, right? So so this is not a rectangle that we encountered before. It's another type of rectangles, and it's very interesting. If you want to compute the integral over this, you want to do it with the region 1 and region 2 type region. It's going to be a bit of work to divide this thing into, it's going to be a bit of work. That's what I'm telling you. But if you want, but here we're going to provide you with a way to do it very quickly. So we would like to see how a double integral looks like on polar coordinates. So here we're going to use exactly the same idea. We're going to use exactly the same idea of breaking it down into small rectangles and And yeah, right? So let me just do the same thing here. Okay. Okay. So this is our rectangle, right? And then we will break it down into small rectangles. Okay. And then small ones here, small ones here, small ones here. Then we will call these rectangles, that is some idea, R, I, J, right? And each one, each point here will be described by, uh, right? We have to choose a random point, a sample point inside the rectangle. We will call it R, I, J star, and theta I, J star, right? And the rectangle R, IJ, will be given by R theta such that R is between, right? R, I, and RI, and then theta between theta I minus theta, theta J minus 1 and theta J, right? So here we're just breaking down this radius R into very small uh, pieces, right? And each one has length Ri minus 1, right? So for example, and then the point here we're going to use is the center of the center of the, so remember it was an arbitrary thing to choose, right? So we're going to choose the center, right, of the of this of the rectangle Rij, right? And then we choose um, the sample point as the center of our function. And this will be given by I star 1 over 2 r a minus 1 plus ri, right? Because you have to take this point plus this point, divide by 2, going to give you the center, right? The center of this of the line. And if you have a line and you have a point and then you have another point, you just have to take the middle point, right? That's the middle point. And then you do the same thing for theta, right? Because theta is something, right? Then you go here, right? Then you have to take the middle point of theta, right? So theta is between, if, yeah, so this will be theta minus, right? Okay. And then theta j will be given by the center of this one, right? So that's exactly what I'm doing. I'm gonna just repeat this thing one last time. If you have this, this here is theta the upper theta, which is theta j minus theta j minus 1. This will give you this angle. When you divide by 2, it will give you the middle, uh, the half of this angle. And then when you do the same thing for r, right? Then you divide by 2, and then you go here. Then it's going to give you the center. That's the center, right? And then of course, this is our rectangle, and this is the center of the rectangle. Okay, cool. All right. And then we compute the area of this rectangle. So the area of this rectangle is, what is the area of the rectangle? It's, these are circles, right? These are portions of the circle. So the area of the rectangle, I, right? It's given by, uh, right? So this is the area of the rectangle, AG. So what we do is we subtract. What is the area of a section of a circle? Uh, it's 1/2 r I squared times delta theta, right? And if you have a if you have a radius, let me just explain this a bit more. If you have, right? If you have a circle of radius Ri, right? And this is delta theta, and this is Ri, right? Then the area of this thing is given by this formula. Then when you subtract, we're not looking for this one, we are looking for, right? They have the same theta, but they have other, different radii. So this is Ri, and this is Ri minus 1. So if you're looking for, so this is the area of this thing, and then you have the area of this thing here, the whole thing, right? So when you subtract, it gives you the area here. It gives you the area here that you're looking for. And this is our Rij, right? So now we have to subtract 1/2 of Ri squared delta theta, right? All right. Uh, mhm. Let me just check if I have the notations good. Delta R. Yeah, yeah, and then just I went a bit faster on this, but the thing is, all of them they have the same delta theta, right? So I don't need to label them. Each one has delta theta. Each rectangle has a delta theta. We just divided this. We just divided this whole. We just divided this whole angle into n delta theta. So we just take, we took all of this angle, right? So each one has, this is delta theta, right? So if you divided n, if you divide it by n, so it's going to be n times delta theta will give you the whole angle. So what is the area? What is the area of this rectangle? It will be 1 times Ri minus Ri minus 1, Ri plus 1. This is the same thing, right? Which will be also, if you go back, this is exactly Ri star times uh, right? So this is delta R, right? We divided like all of these along the radius. We divided all of them into n or m small delta r's times delta theta. Right? So these are the delta theta here. Delta r. All of them they have delta r. So the volume under the function, we're just gonna call it the volume. Suppose it's positive, but just to introduce the idea. The volume under the function f xy is, now you have to be careful because now we're not talking about x and y. We're parameterizing everything with respect to yeah. Ri star is the middle point. This is Ri star was introduced here. So Ri star is the middle. So we wanted to find the middle point of the rectangle Rij. And we wanted to describe this point by a radius and an angle. So what we did is we divided, we did this calculation here to find the middle point of the radius, the middle point of this line, the middle point of this side of the rectangle here. This is the middle point of this one. And then we move along theta just by half of this quantity here, delta theta. I know it's a bit faster, but okay. So here we're parameterizing everything by r and theta, so you have to substitute everything. So once again, we're just gonna do it. So you have to sum over all the rectangles. Uh, so if you choose the middle point, you have to go and find the image of that middle point. So now x of that middle point is r I star cos of theta j star, right? You remember these two here. And then r I star sine of theta star j, right? So this is the image of this point, right? This point. Then we multiply by the area of the basis, and then we just computed this one here, right? So what is the area of the basis? It's r I star delta r delta theta, right? And then you take the sum over all the theta theta. And then you take the sum, you take the limit when n and n goes to infinity. So if you look at our definition previously of a normal integral, this is just the integral of a function f r cos theta r sine theta r, right? Delta, the I, right, over the rectangle R. That's exactly, if you look back. Oh, is there any typo here? I know that ing was the last way to. Let me see. Let me see. No, it's uh oh okay, it's a typo. It's a typo. I see what you mean. I see. But it's the same thing. It's RI, right? Because this is, I went a bit faster, I know, but it's the functions times the area of the rectangle Rij. And this is the area, this is the rectangle Rij. This is the area of the rectangle Rij, and it is given by this, right? And then you just plug it into it here. Same thing. Yeah, it's RPA, yeah. Yeah. So, or in other words, if you don't like BA, you can call it RBR, B beta, right? It's the same thing. But the idea is to look back at this function here and just compare it to the definition of the integral, the one we introduced in the beginning. It's the same thing. And here, delta r and theta will be on the rectangle. So it will be between a and b and alpha and beta, right? F of r plus theta r, then dr d beta, right? So that's the change of variable. Okay, this is a bit too abstract. Let me do an example. Okay. Best, it's the best if we do this in example. And then also it's exactly the same thing as in the rectangles in the Cartesian coordinates. We're gonna have also region 1, region 2, but it's the same thing. Example, evaluate the integral 3x plus 3x plus 4y squared the dA, where to save some time, I'm just gonna give you the description of the region. Right? So we have two circles. Oh, this is also a circle. We have two circles. Okay, let me do it in the where R is given by. So we have two circles. Okay, and here we'll have uh, this here. Oh, sorry. The region here. And this circle here is 1, and then here it's 2. And x squared plus y squared is equal to 4, and this is x squared plus y squared equal to 1. So of course, if you're going to do it with, if you think that this is too complicated, then try to do it with region 1 and region 2 with x and y. It's going to take you a little while. Now, try to do it just with the formula I gave you right now. So what is the region D? So now you have the option of describe it as a rectangle in X, Y, or a rectangle. And in this case, it's going to be very easy to describe as a rectangle, as a polar rectangle. So let us do it. So it's R and theta such that R is between something, and theta is between something and something, right? So let's take a look. R is between R1 and 2, all along the region D, right? Right? So it's between 1 and 2. And theta for each R is allowed to vary from, for example, if I fix some R, right? It's allowed to vary from 0 to pi, right? And this works for all R. Each time you fix some R, it varies from 0 to 2 pi, right? So that's the description of the region. So it's between 0 and pi. Okay, so once you do this, you can now, so by our formula, what is the integral of this thing here? 3x plus 4y squared is given by the A of the region B. Now we have to change everything into polar coordinate. So this will be given by the integral over the region D. Now you have to make sure that 3r cos theta plus 4. Now you have to make the substitution y is equal r sine theta squared. And now you have to integrate, because it's a rectangle, it doesn't matter which order you're going to start with. So dr d theta, r is between 1 and 2, and theta is between 0 and pi. And that's it. Now if you just expand this thing, it's going to give you the 0 pi 0 to 3 r squared plus, no, so, sorry. All right. All right. I make a lot of typos. I should probably work on this. Plus 4. Oh yeah, here is very important. It's R. Very important. This is like a lot of people they forget it. I'm gonna do it like I'm gonna circle it again. A lot of students they forget this thing here. You might be tempted to just just substitute the A by just the R and the theta, and then people they forget R. Yeah, between 1 and 2, and then they forget R, and then it doesn't give you the right thing. And of course, this is not a competition error, so don't expect to get any extra points. Or this is a conceptual error because the area doesn't translate into the R theta. There's a factor R that plays the role here. Okay. Okay. Right. So it's for the power 3 VR b theta. Okay. What I'm not gonna do it. This is we've been doing this. Well, and you do it. It's very straightforward, except for this one maybe. You have to use the formula uh, cos 2 theta is equal to cos square minus sin square 1 minus 2. Right? Is it this one you have to use it? And it's supposed to give you this number. Okay. Right. Should we take 3r 3r squared? Is it? Yeah. Oh, sorry. Yeah. Okay. Should we take a break right now, or do you want me to finish at 12:50? I still have to give you what happens when the boundaries finish. Okay. If we think I think we should finish. Yeah. Okay. Let's finish. So we did. So this is a rectangle in the polar coordinate. So the exact same idea as we did with the type 1, type 2. Translate literally to these polar things. So for example, if I have in the region D and right. So if, for example, I have some two angles, right? But instead of a line, because a line in polar coordinate is a circle, instead of a line, I have a function like this, right? And then I have another function, right? This is exactly the type 1 and type 2 things. You just have to, if you understand that way, you're gonna understand this way. The answer is 15/2 pi. What is supposed to be? Uh, what is an integral? And in this case, it's not going to be the volume because x is not necessarily, because this one here is not necessarily positive because it's inside this region here, and x can be, you have to look at it. I don't know if you're asking about the conceptual uh, meaning or, but anyway, it's 15 pi over 2 if you're asking about the answer, and it's not necessarily the volume if you're asking what's supposed to be. All right, so let's go ahead. So the exact same thing applies if you have some fancy function here. Of course, it's going to depend on uh, theta, right? Because now r will be given by theta, and then here, right here, it's gonna also vary depending on theta. And you will have here, it's a bit more straightforward as like, uh, right, for some theta, right, for some theta, you will have to vary from this thing to this thing, uh, right? So this is a region D. So more, I still have 10 minutes. So more general regions look like D is still described as a couple R theta. Just that theta will be allowed to vary. For example, if this one is alpha and this one is beta, right? Theta will be allowed to vary from alpha to beta, but the only difference is once you fix theta, R does not have the same boundary as in the rectangle case. It's going to be some fancy function here, h1 theta, right? It depends on theta. The first, the bottom boundary depends on theta, and so it goes for h2, for the top boundary, h2, right? And this will be the function h2 theta, right? And this will be the function h1 theta, right? And you can do the same thing with the function bounded by a rectangle, and then do Fubini, and then all of that. And then it's going to give you, for this kind of regions, and these are only one of these simplest way, the polar coordinates. So for this kind of regions, the integral, so the integral over D will be given by the integral. Okay, so this will be the integral over D of a function fx dA, okay? Uh, then you have to substitute everything. Then here it's going to be f r cos theta, r sine theta, and then don't do the mistake, r dr d theta. And now r will be between h1 of theta and then h2 theta. and then theta will be allowed to vary from alpha to beta, right? So an example of this, will be, I'm not gonna write anything, I'm just gonna give you the region where this applies. For example, if we are on the, right? Suppose I have suppose I have a sphere, x squared plus y squared equal to 1, and the cone z equal to square root of x squared plus y squared. And we would like to find uh, the solid between them. So the sphere will look like this, right? That's the sphere. And then the cone will be given by something that looks like this, right? If you find the intersection, you have to do the same thing here, right? And then you will be asked to find the, the boundary cone, yeah. And then we are asked to find the volume of this solid here, right? That's the volume. Like find the solid here. This is, we're gonna call it the solid S, right? Right? And here we have Z equal to x squared plus y squared. And here we have the sphere x squared plus y squared plus z squared equal to 1. So we have to first find the intersection. This, right? Uh, First find the intersection. I have 3 more minutes. Can you scroll up a bit? Yeah, here. I have 3 more minutes, and I don't know if I should be going quickly or, but let me just explain in 3 minutes what we'll do. So here you can do it by x and y, right? You have the, but then it's gonna be a bit more work because then you have to isolate z, and then you have to find d, the region d. The region, the way you do this is you have to project on the plane, right? You have to project on the plane this small region here. It's gonna be another circle, right? Right? It's gonna be another circle. That's the projection. It's gonna be another circle. And then you will have to subtract in this case. Okay? I don't think it's a good idea if I go very quickly on it, but yeah, that's the summer class. I can see you until next week. Yeah, but this type of, when you project, the region D here will be best described using using the polar coordinates. Okay, here you will have to in polar in polar coordinates, D is given by, so the point is to make you observe that if you want to describe it with X and Y, it's going to be a little bit hard. D is given by, yeah. So you have to find the intersection of these points, right? And then this is just Z equal to Z, and then solve and solve and solve. It's going to give you um, the intersection will be in this case a circle. Its intersection equal to x squared plus y squared is equal to 1 over 2. You just have to equal z equal to z, and then you realize that it's a circle. And then when you project on the two planes, this is x and this is y, you will have the same circle. So D will be all the elements r theta, such that, so for a disk, this is a disk, right? When you project, it's between something, and theta is between something and something. So if you look at it, it will be between 0 and 1 over 2, right? Because that's not 1 over 2, it's 1 square root of 2, right? Because the circle, this is the equation of the intersection. So what is the radius is 1 over 2, right? So this is the radius, r is equal 1 over square root of 2. And then theta is allowed to vary freely along inside the disk. So it's between 0 and 2 pi, right? And yeah, it still have, so this is me just to write down what is the integral. I'm not going to compute it. And then I will let you go afterward. So the volume, once you find the region B, so the volume is, you have to compute the volume of over the region B uh, of the surface above B and under the sphere, which is square root of 1 minus x squared minus y squared, right? Right? So this will be the region, I would say this one, sorry, right, sorry. So this will be the region with all of this. I hope it's gonna be clear. It's gonna be the region here, right? Right? And then you have to subtract the volume under the cone, right? Right? And this will be, with me using the color, and I hope that's not going to be ugly. So the volume under the cone will be this here, right? All of that. So if you look at it like in 3 dimensions, that's exactly. So when you subtract these two, it's going to give you the green one. I know it's not the best, but it's the best I can do. So when you subtract these two, it's going to give you the green one, the little shell that is just between the cone and the sphere. And then so concretely, this will be equal to, so when you substitute everything with the region and all of that, it should be given by the integral from 0 to square root of 2, from 0 to 2 pi, and then you will have to, and I'm using all of the properties of integrals, right? R, dr, d theta, and then you will have to substitute everything, right? It's 1 minus r squared plus square theta minus r squared sinus squared minus uh, r cos theta plus r squared sin theta. Okay, and then I'm sorry, we didn't have time. It's already I'm taking a lot of your time. I'm very sorry, but you should be able to do this. This is not anything hard. We're not gonna do it right now. Uh, we were supposed to do applications of double integrals, but in any case, there will be some introduction to this in the problem set. And the next week, hopefully, I'm gonna go over this quickly. Nothing new. There will be nothing new. It's just a couple of definitions. No, we didn't have time to do it now. Not, yeah, it was a bit hard to go faster than this. Uh, so it's a couple of definitions, and I will make sure that you know which if you have any problems that you know with the definitions. It's a couple of definitions that nothing new. You will just have to apply these integrals to some definitions. It's really nothing. It's interesting, but it's nothing new. It's definitions and understanding the concepts. Yeah, and I hope that next week I'm gonna go over it quickly. Yeah. So the volume we're trying to find is uh, is this one here, the one with the green. So that's the volume, right? The green one. Can you explain which part minus which part from the previous again? Okay, let me do it. Let me do it again here, since you appear to be interested, and I don't want to take all of your time. Let me do it again. Okay. So we had our three acts. Okay, and we had our sphere. I try to use colors just in a hope that it will make things very clear, right? So we have our sphere, and then we have the cone that you can see that. Okay, does it make this? No. And then we have the cone here. Okay, that's the cone. Okay, and now we wanted to find the volume of this very small region here. Okay, under the sphere and above the cone, right? Now, what we do is we projected this circle here, the intersection. We projected the intersection on the plane, on the x plane, which gave us a circle of radius 1 over square root of 2. Okay. Okay. So that's the circle. Let me just be. So that's the circle we had, and So what we did is we took this, okay, let me change the color again. We took this volume here, right? That's the volume we took, right? And then we subtracted this volume from the volume here under the cone. Let me see. Is it clear? All right. We took this one and we remove this one. Yeah. So we took that one and then we removed the one under the cone. Yeah. And then we remove this one under the cone. But wait. Uh, we took this volume and then hmm, okay. Oh, okay. I was not really clear. Uh, that was not, yeah. We when you remove this one, yeah. When we remove this one here, thanks for asking everyone. So yeah, it was a bit faster. Um, when we removed this region here, it gave us exactly the solid between the sphere and the cone. And there will be something inside. It's not just this very little shell here. It's also the one inside, right? So when we remove this part, we still had some inside, right? It's kind of ice cream thing that in spoon form, uh, right? It's an ice cream form. That's the volume we computed, right? But that was just uh, specific. You can also remove the other one. All right, any other question? I hope it was clear. So the final answer will include the volume of the bottom portion of the cone. Yeah, it will include the, yeah, exactly. No, exactly. That was a mistake. That was not the question. That was not the question. The question was to find, let me just look at the question again. The question was to express the volume of the solid between above the cone and below the sphere. So it's above the cone, right? So this is the cone, right? Right? So it's still inside the cone, right? It's something here, but just below it. The one I gave in the beginning was just this part here, which is between the sphere and the plane. Uh, we just have to find z such that they intersect. You know, so that was not that was between the sphere and the plane. The one we're looking for is between the sphere and the cone, which will include a portion of the cone, the inside of the cone. All right, hope this is clear. Okay, everyone, thanks for your patience and see you next week. Bye-bye.